Hello everyone, welcome back to the All About Data YouTube channel. In this session, we are going to discuss an important topic, performance optimization in Snowflake. Performance optimization focuses on improving query speed, reducing execution time, and making efficient use of compute resources. In this video, we will specifically look at three key areas: warehouses, caching, and clustering. These components play a major role in how quickly Snowflake processes queries and how well it scales for different workloads. Understanding how to configure warehouses properly, how caching works behind the scenes, and when to use clustering can significantly improve overall system performance. In the upcoming slides, we'll break down each of these concepts step by step with clear explanations. Let's get started. In this slide, we are discussing the virtual warehouse strategy for performance optimization in Snowflake. The first key concept here is isolating workloads for performance. On the left side, we see Warehouse A, which is used for ETL or heavy data loading. ETL workloads consume a lot of compute resources, and if they run together with reporting queries, performance becomes slow. On the right side, we see Warehouse B, which is dedicated to BI and reporting. By separating ETL and BI into different warehouses, reporting users get fast and consistent performance even when heavy data loads are running in parallel. The important takeaway is to never mix heavy ETL workloads with reporting workloads, because resource contention can slow down critical dashboards. The second concept shown on this slide is leveraging caching for speed and cost. When a user runs Query 1 for the first time, the warehouse executes it normally. The result of this query is then stored in the 24-hour result cache. If the exact same query is executed again within 24 hours, Snowflake returns the result instantly from cache without using compute. This means zero compute cost and much faster query response time. Together, workload isolation and effective caching play a major role in improving both performance and cost efficiency in Snowflake. In this slide, we are understanding micro-partitions and pruning in Snowflake, which is one of the most important performance optimization concepts. At the top, we see what Snowflake calls the secret sauce: automatic data splitting and metadata. When raw data is ingested into Snowflake, it is automatically divided into micro-partitions. This process happens internally, without any manual partitioning. Each micro-partition stores metadata, such as minimum and maximum values for columns like date or ID. When a query is executed with a filter, for example, a where clause on a date, Snowflake uses this metadata to identify which micro-partitions are relevant. Only the partitions that contain matching data are scanned, while the remaining partitions are ignored or pruned. This significantly reduces the amount of data scanned and improves query performance. Pruning works by skipping partitions that do not contain the filtered data range, and this approach is often faster than using traditional indexes. At the bottom of the slide, we see how to check pruning effectiveness. By looking at the query profile in the UI, or by checking query history, we can compare partitions scanned versus total partitions. A large difference between these values indicates effective pruning and better performance. In this final slide, we are discussing clustering keys and how they help improve performance by forcing data order. First, let's understand when to use clustering. Snowflake automatically manages micro-partitions, so clustering is not required for every table. Clustering becomes useful for very large tables, usually in the terabyte range or higher, especially when queries repeatedly filter on specific columns. A good candidate for clustering is a table that is frequently queried using a column like event date, but where data is loaded in a random order. In such cases, clustering helps organize data so related values are stored closer together. On the right side, we see how to define and monitor clustering. A clustering key can be defined at table creation time, or it can be added later to an existing table. Snowflake also provides a way to monitor clustering effectiveness using system functions. One important metric to watch is clustering depth. A lower clustering depth indicates that the data is well clustered and queries can prune data more efficiently. To conclude this session, we learned how virtual warehouses, caching, micro-partitions, pruning, and clustering work together to optimize performance in Snowflake. In upcoming videos on All About Data, we'll cover query tuning techniques, query profile deep dives, and real-world performance optimization scenarios. Stay tuned, keep learning, and thank you for watching.